IT journals. He's also an editorial board editor-in-chief of iManager's Journal on Embedded Systems, Energies Journal MDPI, and the subject editor for the IET Renewable Power Generation, IET Generation, Transmission and Distribution, and FACTS Journal Canada. I welcome you, Dr. Padmanabhan. Please.
Thank you very much for this invitation. Good morning to one and all. And personally, I thank to High Manager and its management, includes Mrs. Renisha, for inviting me to this conference for to share my views on my research activities. Before I go for my presentation, I like to show you something about Aalborg University, where I'm working. Could you able to see my screen? Are you able to see my screen?
Yes.
Okay, so this is Aalborg University in SBR campus, which is the southern part of Denmark, and this is Aalborg University, which is in Aalborg. And about facts, we are having different research and education programs in humanities, social science, medicine, engineering science, IT and design. Of course, we have a student strength around 20,200, 2,280, 850 part-time students, 850 PhD students. And about the strength of the resources will be around 2,230 staff members, 690 international researchers, 1,270 administrative staff, and around 450 million US dollar is the annual turnover. About Denmark, so Denmark is a small country where Aalborg University is located in Aalborg, and I'm working in Esbjerg, which is southern part of Denmark, and we have another campus in Copenhagen, which is the capital city of Denmark. So, and the human capacities and staff members are shown here, and each campus is what we have. And about Aalborg University, we have a specific scheme in teaching methodology, problem-based teaching methodology, project-based teaching methodologies. Aalborg University has been ranked among the top 5 in the world with research and, of course, in teaching methodologies. About learning goals, we are working on a problem-based learning or project-based learning. And in every semester, student will have particular courses. At the end of the courses, they have to execute some projects in real time along with the supervisors. Usually 50% of the projects are from the industries and for research as well as for the master degree and bachelor degree programs. About the recent cases, 35 case stories are readily available, which shows the strength of the Aalborg University, how the research reflects the societal needs and carrying the society for the next level. And about research, Aalborg University is always a top university in research publications. This year, recently, the Aalborg University has been lifted to #1 in electric and electronics engineering and #6 in overall engineering. In Times higher education ranking, we are around 207, and among top 20 ranks in Young University, which is considered as 50 years less of inception. Aalborg University always retain its ranking in top 20. And about SBR campus, we have different programs. For electronics, we have advanced power electronics. Bachelor programs, we have sustainable energy engineering. Masters includes offshore energy systems, process engineering, combustion technology, oil and gas, and risk and safety management. So these are some of the signature programs which are available in Aalborg University for pursuing master programs. Apart from that, we have also chemical engineering, bioengineering, construction, and etc. So you can visit all these program details in Aalborg University website. With this small introduction, let me move on to my technical session, which is I'm here. Could you able to see my screen? Could you able to see my screen? Could you able to see my screen? Okay. Okay. Because I have 2 desktops. So today I like to present some research activities we have done in my own research groups for cost-effective solutions of EV and microgrid applications. So today, renewable energy become a major part in adoption of EV or a smart grid or microgrid, because without power electronics, it's not possible to connect these 2 mediums. And of course, power electronics converter play a critical role where we develop some novel solutions. I can show you some experimental orientation, how we validated these systems and how it can fit to the EV applications and renewable. And of course, there are a lot of challenges. I go directly towards the application because there are a lot of theoretical background behind these research activities because it can consume a lot of time. Better, I can show you directly how we have been working with the real systems. Most of the microgrids are essential now in developing countries. Of course, in developed countries, of course, wherever the power cannot be delivered to the remote areas like India, Brazil, Africa, and South America. So we need to utilize the local energy resources which is available in each sites. In particular, renewable energies can be from fuel cell, photovoltaic, wind, batteries. And batteries are used during a peak generation of power from the sources can be stored and it can be delivered to the load when the load requirement is in high peak demand. Of course, the renewables can be between 24 to 48 volts, and the common point of coupling, which is a grid, going to be around 400 to 800 volt. And application can be most effectively electric vehicles, DC microgrids, DC home application, and existing AC microgrids. In these all cases, we need a power electronic intermediate electronic equipment, which has to withstand all these variation, either if there is a low power from the input from the renewable or there is a fluctuation in the load, on all these stresses has to be handled effectively by power electronics converter. So we done several original configurations. In this case, we introduce a three-state model. Why we call it as a three-state model? Because we have three devices and three MOSFETs turned on at different states. If you look at very closely the structure, if you look at, this is a load side converter, it's a standard boost converter. A boost converter will convert a low voltage to very high voltage. If you look at the source side, input side converter is a standard inverter, and one of the devices is replaced by the inductor in the phase A and also in the phase B. So we have a single phase system. And when we are triggering with the different duty cycles, these energy available on the renewable can be delivered with a high potential to the load side. Once we design the converter, the most important is to know what is the parameter, the gain, which we can able to derive from the existing sources when compared to the previously available converters in practice. So we try to figure out from 10% to 60% utilization of the renewables, which is connected on the input side. Around 60%, we are getting a gain of 42, so it's very high. Simple language, I can say if you keep an input of 10, you will get 420 volt at the output. Once the converter is designed based on the theoretical background, then the performance test has been carried out for utilizing the gain margin of the devices with the DC bus. Then the most important is the losses, because we have to look at the losses, what are the produced from the converter in real time. Of course, we will have losses produced by all the two inductors, LX and LY, around 17%. On inductor, and we are going to have losses by the inductor Z is going to be 16%. Diode is going to be between 4.8 to 5.2 percentage, and capacitor losses is around 6%, and the inductor internal resistance loss is around 9%. So this gives you a complete scenario how the losses has been generated. Where to find these parameters? These parameters are readily available in the data sheet which the company manufactures the component, because we are the researchers, we are not manufacturing the devices, we are utilizing the devices which is available in the manufactured by the industry. So these details are readily available. The spectrum analysis can be easily done before the real-time implementation. And most important is the validation. So we found out then experimental testing. As required for the common point of coupling, we are generating around 400 volt exactly. And these are the results of the current through the input inductor, and it shows a clear spectrum. There is no any huge distortion or unwanted behavior. And this is the voltage across the device MOSFET, and it goes to a peak of 185 volt, whereas your input is only 24 to 48 volt. And this is the voltage across the diode, which is connected for a forward bias condition. It behaves as expected, and the peak goes to 185. So these are the cross verifications. The performance has been retained for the expectation of connecting to the renewables towards the load application. Then the second case is very important because loads are not fixed. They are like fluctuating in nature, because one, for example, I can give you an example. One house can utilize 100% power. Another house can utilize only 25%. So there is a big fluctuations, but all these fluctuation has to be controlled by the power electronics converter. So we try to figure out the regulation from a maximum to a minimum value. You can see a 395.2 volt. It's not 400 volt because there is a losses, and towards 206 volt. Whereas the input is kept always around 30 volt from the batteries or fuel cell or from the PV. And in all the cases, if you look at the input current is always regulating with respect to the theoretical background, what we design, and it is very smooth that ensures the reliability and durability of the renewable which is connected on the input. So this current plays a critical role to ensure all these parameters of your renewable for utilizing long time application. And these are the close views of the input current shown at different regulation points. The behavior is very smooth, doesn't have any sort of high deviations or hazardous effects. And of course, the amplitude obviously changes because we are regulating the load. How we done these things? It's very simple. We are controlling the duty ratio of the each devices. First case, we kept the devices around 50% and 35%, one device and another device. Last case, we kept 35%, 35%. So we are utilizing only 35% of the supply from the DC bus. This case, one is 50%, another one is 35%. These are some of the experimental developments we have carried out with our students. We have power electronics converter. You can have a look. What is the size of the converter? It's very small, very compact. That's why I say it is a cost effective. If some component fails, maybe inductor or the capacitor or even a semiconductor devices, can be easily replaced. Cost wise is very cheaper. Or you can replace the complete stack. Simple solution because it's very cheaper. And these are the digital scopes we are used to capture the results and with the resistive loads. And few results are shown here for the clarity. The input is around 30 volt and the output as expected 400 volt is generated, and you can have a complete look on the input current. Why we are specific about the input current? Because this current decides ensure the efficient reliability and durability of long time application of your renewable which are connected on the input side. And these results are taken for 250 watts, and these results are taken for 350 watts testing in laboratory scale. Further, we also develop other converters like a quasi-Z source converter. If you look at very closely the converter, the load side is going to be a standard boost converter. And on the input side, between the source and the load side, we incorporated additional inductors, and we technically call it as a switched inductor, because when the device is on, the instantaneous energy available in these two inductors will be stored in the capacitor as a potential difference, so that we can able to generate a voltage here, and the energy available will be in this inductor will be stored in this capacitor. Now all the capacitors energy are delivered to the load capacitor through the MOSFET, which is triggered as a boost converter. So you'll have a very high voltage from this point of view because you have a boost converter, and of course additional energy stored in the capacitors. And this can be visualized from here because the capacitor C1 goes to the peak value of 66 to 65 volt fluctuation, 1 volt ripple. And second case is around 120.5 volt to 119 volts of 0.5 volt. Last case is around 2 volt, 65 to 63. So we show a very clear expected performance of the capacitors, which is behaving at different intervals of switching. And the next stage is very important because how to utilize the maximum gain. So we are trying to use the devices from 10% to 30%. In 30%, we are getting around 22 times the input. So the gain is very high. The next stage is the loss analysis. Without the losses, the converter produces the maximum power, goes to 200. In practical, yes, we are going to have various losses, passive and active component losses. When the losses are incorporated, then it is around 194 times the gain. And of course, we introduce some simple converters by making a simple modification how to enhance the power. In this case, if you look at very close, this is a standard CIPIC converter, but we included two inductors and two capacitors, two diodes and two inductors and capacitors in this fashion, so that these two diodes will control the flow of current. Whatever be the energy stored in this inductor will be delivered to the capacitor, similarly from this inductor to this capacitor, so that you are going to produce a very high voltage across C3. Simple solution. So it's a boost converter with a combination of diodes and capacitors. Once the converter is designed, the next stage is very important to look at the various losses. The switch, the MOSFET produces around 47%, and diode is around 12% to 13%, and inductor is around 10%. Of course, LY is around 1%, and capacitor is 5%. The combination of LZ, C2, C3 is around 0.4%. So we have the complete distribution of various losses which is produced by these components. The next important thing is the efficiency, because we are trying to figure out from 60 to 100 the maximum output power. So obviously at maximum power you get maximum efficiency, because the rated condition 91.4% efficiency. Remaining all goes because of these losses. And of course, we are not powering all these converter due to the safety reasons and the protection, and of course, to ensure the testing, we are operating all these high power converter at very low power. And the input is around 24 volt. We kept in from the renewables, and the load is around the 0.1 ampere. And this is the input current. You can have a look at the complete smooth propagation, so that, as I said before, all the renewables are well protected. And this is a load voltage. This is around 172 volt from 24 volt input. So there is a big boosting, or I say step up from input to the load connected voltage. And this is all performances are taken on that linear operations. Then the most important is the non-linear condition. So we technically say discontinuous mode of operation. For a non-technical person, I say it's a non-linear condition, because even an inductor behaves a non-linear property during the switching. So that's why DCM is very important. In this case, we are looking at the diode. The diode voltage of 3 level. This confirms, yes, the peak goes between 192 volt to 150 volt. We have 3 levels, so that is operating in DCM mode. And second possibility, you can compare with the inductor current, which goes to 0 and the peak. Similarly, for the inductor, you can see here 0 to peak. So on this, even under this huge discontinuous mode of operation, the converter is able to deliver a 92 volt irrespective of relatively input 24 volt. Further, we also develop many converters based on existing solutions. This is a standard off-bridge inverter, which is available in the industrial perspectives, which is connected with additional components which we framed, like capacitors and diodes, and we call it as stage 1, stage 2. We can have until n stages, and it can be connected to the inverter, then to the motor, then to the grid. So you will have a AC DC voltage, very high DC voltage can be connected to the inverter. Of course, we can also connect to the battery for the charging. During the peak demand of the load, we can take the power from the battery towards the grid. So these are the applications of using these converters. And if you look at very closely the components, if there is a 0 component, there won't be any stages, so that your converter is going to be a standard off-bridge inverter. When you're going to increase the number of stages, for example 6, then you are going to have 12 diodes and 12 capacitors. What is the advantage of this configuration? We are not using any transformers or huge number of components, semiconductor devices, only few, so the controlling is very simple. You can use any digital signal processor, even with low frequency operations. But if you are connecting for a grid connector, then you need a sophisticated digital processor. And about the gain, when you are utilizing the gain from 10 to 90%, we are going to use these devices from 10% to the 90% utilization of your DC bus. Obviously, at 90%, you are getting maximum gain. In real time, it's very important how these are applied. In case of conventional solution, we have PV, wind, and battery, and these are connected to DC-DC converters and to a common point of coupling, and to an application like electric vehicle charging or AC motors or grid connected application through an inverter. But for a windmill, the output is not AC. It's going to be it's not going to be a DC. It's going to be AC. So we need an additional converter which converts AC to DC, then to DC-DC, and connected to the common point of coupling. This is an existing classical model of microgrid. How to minimize the number of converter? We can use one converter which can be able to connect all the multiple inputs and can deliver to the same application of the conventional systems. In this case, we propose something like a 3-port network for initial test. So why we call it as a 3-port network? Because 1 output port, 2 input port. One can be a PV, one can be a battery. And this configuration is derived from a standard boost converter in combination with standard industrial converter. So we matched together and adjusted the configuration through the diodes and switches so that you can able to connect multiple inputs. This configuration can be extended to have multiple inputs. What is the purpose of this converter is always to keep the maximum power point available from each renewables and batteries, because PV can be produce maximum energy during the daytime, whereas the wind can produce during when the wind is available. So the input power are fluctuating. So in this case, the electronics converter has to keep the maximum power delivered to the load. So if the power is going on clockwise direction or anti-clockwise directions, by adjusting these devices, semiconductor devices, the power of the will be maintained at the maximum value. And these are some of the experimental results. You can have a look. PV is around like a battery, 12.5 volt is kept, and we are having a current around 7.9 amperes. And the output you can have it's been doubled. 24 volt has been delivered to the load with a load current of 3.6 ampere, keeping a duty ratio of 60%. We are utilizing the DC bus, I mean the PV panel. And these are some of the triggering pulses which is developed from the digital processor controlling the MOSFETs. And these two are the current through the inductor. I said it's very important to ensure the reliability and durability of your renewables are very smooth. In this case, we tried to figure out for 40%. So 40% also the response is the same and it's very effective. And about the output, PV is kept around 30 volt and input current is around 800 milliamps, whereas the output is reduced to 18 volt. So we shown two possibilities. One is output voltage is very high, and the second case output voltage is very minimum. And the load current is around 980 milliamperes. The next important is the efficiency. If you look at very closely, we are using a duty ratio between 20% to 80%. And this is a numerical simulation model. You have very high efficiency because there is no losses in numerical softwares and considering all ideal conditions. Whereas in the experimental solution, the efficiency comes around 93.6% as expected because of various losses. Now, how we are doing all this control? We have the converter which is proposed, trying to figure out the current from the PV battery voltages from battery and also from PV and output current and output voltage. All these are given to the multi-objective controller, and the multi-objective controller develops power flow direction, battery management, mode of operation, and duty cycle, which controls the MOSFET devices. The program is started. We are trying to check what is the power from the PV. Where it is greater than 0, you can go to the next step. Check the power of PV greater than output power. Go to the next step. Battery current is greater than battery max. Then go to the last step. PV can connect to the load. If the first step fails, you connect the battery to the load. If fails the second step, connect battery plus PV to compensate the power to the load. If you are failing the last case with the battery current, check for SOC state of the charge is 90%, then no issue, you can connect to the load. If less than 90%, try to connect PV to battery to charge the battery, then to the load. It's simple management. Recently, we developed this big power electronics converter. It looks like a big, but concept is very simple. The load side is a standard boost converter, which is available in the industrial application. As I showed in the first slide, the standard inverter, half-bridge inverter. One device is replaced by inductor. And the second leg, we introduced one MOSFET along with the inductor and capacitor. And these leg can be extended to N level for increasing the input voltage of renewable to a very high value and to give us an input to the standard boost converter. If you look at the power from 100 watt to 500 watt, in numerical simulation, we are get around 94% and near to 97% efficiency, whereas in case of simulation, it is less than 94% because various losses due to passive and active components. What is an application? This is an application. We have common point of coupling, 400 volt DC bus. So we can have wind. The wind can be connected to a rectifier, from rectifier to the inverter, then to again a rectifier. It can be connected to a DC common point of coupling. Other possibility, we have a standard AC transmission lines, which can be connected to AC voltage regulator, then to rectifier, and can be connected to the common point of coupling. And the last one is the battery. Battery can be connected through the inverter, then to a rectifier, to a DC grid. So this can be charged during the power available peak from the the renewables or transmission generation systems, and stored energy can be again delivered to the load when the load is requirement is very high. Other side, we can have electric vehicle charging station. Of course, the electric vehicle can also feed the power to the grid, because nowadays end user or become entrepreneurs, and this can be possible through a DC-DC converter. PV panel can be connected through a DC-DC converter to power the microgrids. Other possibilities, we are having applications like iPod, cameras, etc., televisions. These are powered with DC home applications. Obviously, whenever we develop the converters, the experimental and numerical modeling is very important. First, we try to figure out in numerical modeling. The input is always kept at the required of 40 volt, and the output is around 400 volt, and output current is around 1.4 amperes. And these are the currents through the inductor, which shows a very smooth propagations. And these are done for to show the performance of the converter, how it behaves in real time with an experimental results. The input voltage is kept 40 volt. This is the input current, very smooth, no issues. And output voltage is generated around near to 400, but is not 400, it is 394.6 volt because of the losses. And of course, this is the current. And we have shown also the capacitor voltages, because capacitors can be it can break very easily because of the small spikes or small deviation in the voltage. It ensures the voltages are very smooth so that the capacitors are working appropriately for its long time utilization. And this is the output voltage, and of course we have shown the current again. And in this case, numerical test shows the same performance in correlation with the experimental value. Finally, what is an application? An example is electric vehicle. If you look at electric vehicle, because most of the countries are focusing towards 100% electric vehicle, one of the possibilities to use fuel cell instead of using conventional IC engines. So in case of fuel cell, we can have a fuel cell generated DC voltages here from fuel storage tank, which has a hydrogen, then fuel reformer, to fuel cell for getting DC voltages. But this DC voltage has to be connected again back to your DC-DC converter, then to an inverter to drive your motors. Of course, to use other applications of luxury in electric vehicle, we need additional DC-DC converters. If you look at very closely, the efficiency is around 80%. So the electric vehicle, if you design, the major part, critical play is done by electronics converter with around an efficiency of 80%. Other possibilities, we can have a combination. So we call it as a hybrid electric vehicle, where we can have fuel cell. Of course, we can have a battery or ultra capacitors store large DC voltages and currents. In this case, again, we need a DC-DC converter. It should be efficient to charge the batteries or ultra capacitors. And the stored energy has to be driven for the purpose of driving the motor when it is required. So it's like a sharing the power between fuel cell and batteries. Of course, these cases also the efficiency is around 80%. The next application can be transportation, because transportation is very heavy. And in this case, we have two types of transportation. One is low duty vehicles and heavy duty vehicles. Again, in low duty vehicles, we are going to have fuel cells. The power generated from the fuel cells will be given to the DC-DC converters. Then we have a battery units, which is powered through the electronics DC-DC converter. Then inverter to drive the motor. Then we have additional DC-DC converter to control the luxurious needs of the vehicle. Luxurious needs means light, air conditioners, airbags, ABS systems, and other protections, etc. All are done by electronics converter for triggering and control. This is an example of a heavy-duty electric vehicle where you need a DC microgrid within the vehicles. So we have a fuel cells, then we have electronics converter, which can control the luxurious need around 25 kilowatts. The fuel cell output is connected to the DC converter to a common point of coupling, and we have batteries around 600 to 700 volts with battery controllers. From the common point of coupling, we can have an inverter to connect the motor to drive all the wheels, and another inverter to control around 20 kilowatt power, which can be fed from the DC microgrid. Then we have motor controllers. So you can have a complete look how these electronics converters play a critical role in EVs and to make more efficient. So we've done many power electronics converters, particularly 1, 2, 3, and 4 topologies, because we develop many configurations. At the end, we find that XY is better because high reliability, average cost, high efficiency, And most important is single semiconductor device is used and structure is extendable, whereas the drawback includes a discontinuous input current and large number of diodes, so that you will have more losses. But it can be applicable for heavy duty and low duty vehicles. Always the comparison is with standard solutions. Standard solution is resonant converters or transformer based converters. If you look at the reliability is going to be average, cost is very high, and efficiency is very high. Of course, the advantage, we can have a high power application with soft switching, and because of the transformer, the turns can be tunable. Disadvantage, bulky, more losses due to the magnetic components. An application can be for high power and high duty vehicles. So this is a standard solution available in the practice. We are comparing with our own investigation results to find a suitable solution, which can be cost effective as well as cheaper. Sorry, cost effective and more reliable. In case of challenges, finally I come to challenges is very important. How to improve the efficiency? So when it's an renewable or it's going to be a electric vehicle, as soon as possible, how much we are going to adapt electronics converter to replace all the mechanical and hydraulic parts, then the efficiency will be improved. Because one way we reduce the cost, another way we are reducing the sizes, compact structure, and there is a fault, it is readily replaceable because semiconductor devices are cheaper cost when compared to a mechanical hydraulic shafts, hydraulic parts. Of course, the selection of PV, fuel cell, and battery plays a critical role in microgrids for its efficiency, how we are selecting the components. And for electronic circuits, EMI play also a critical role. Electromagnetic interference need to be compensated along with control strategies. How to increase the durability of renewable and EV? Again, the challenges lies with especially for batteries. How the electronics converter is connected. I already discussed several times about the input current. So the input current decides the long time of application of your battery. So we need to keep the battery proper charging and discharging level by controlling the state of the charge. And semiconductor devices, its lifespan decides, so that we can able to use these semiconductor devices for a very high vibrations and high thermal flow of current. Because of the flow of current, there will be high thermal effects. So we need to provide a proper cooling systems to make these power electronics converter can be used for a very long time. At the end, it's very important, obviously, high efficiency, low cost, small size, and rigidness or a critical play for durability. How to increase the performance of the renewable? Always the controller plays a critical role, because the controllers are the executors of the pre-programmed instructions. And in this case, what type of digital processor is used, how much fast enough to respond to the uh, environmental actions, that's very important. In case of safety, again, a critical role will be played by the um, digital signal processor, because it has to detect the parameters from the stator, rotor, bearing, and for example, nowadays EVs with ABS system and airbag, usually electronic actuators are used. In the past, it was hydraulic unit. So if there is any problem comes, it can be easily replaced, and it should be very fast because the signals are coming from digital signal processor. So the sampling rate should be very high. And how to reduce the overall cost, that's always very important, because it's going to be very challenge for the electronics engineers. We need luxurious to be maximum for an electric vehicle or for any applications of DC microgrids, but cost should be very low. So the selection of electronics components, of course, the selection of PV, battery, etc., fuel cells plays a critical role how we are selecting. And the most important is the high quality performance and reliability with all this cost reduction. Finally, I conclude my presentation. We have investigated several configurations for renewable energy applications, and of course for fuel cell based electric vehicles, where the electronics converter can be adapted for high voltage generation, and irrespective of the low prototype renewables. And in this case, of course, we can say hybrid and multi-port converter are more effective, because you can have multiple inputs. Hybrid converters can have multiple configuration with minimum number of devices and components, unable to generate high voltage. All these cases very important. The cost is very minimum, number of component is less, and it is modular structure, and controllability is very easy with digital signal processor. At the end, our aim is always focused on eco-friendly systems with zero emissions, high power capabilities for renewables and EV, and of course with lower cost. Thank you one and all. If you have any question, I'm happy to respond.
Thank you, Dr. Vatmanaban, for the wonderful presentation. I would just like to conclude a few words because the purpose of any research is should be helping humanity. So we have come a long way from the invention of the wheel to electric vehicles. From bullock cart and hand-drawn vehicles, we have moved to electric vehicles over the past so many years of the human evolution. So we look for a time when there would be a time that would come to have more cost-effective electric vehicles because we know Tesla has come, it has arrived, but still there is a research orientation towards more cost-effective electric vehicles coming, and this could be a great indicator for reducing environmental pollution, the greatest thing that the humanity is facing nowadays. So I hope like more research will be happening in this field, and your research has been a great eye opener. Thank you very much.
Thank you. See you all. Bye. Take care.